So, okay, we reduce this. Okay, the students of, I think all the diploma students are already there. Yakubu, Dang, should be okay. So do you remember last time we discussed the method, how to estimate a dispersion curve using seismic noise? And we mentioned that this can be done calculating the correlation between the signals recorded at many stations of an array and using the noise coming from many directions. And this is done using, again, an approximation in the frequency domain. So all the signal are first transformed in the Fourier domain. So what we were seeing is that this is my signal at one station, and this is the signal at another station. Operatively, we divide the signal in a certain number of windows that we call here M, that are simultaneous. So the window 1 starts exactly at the time of window 1 on station 2, and so on. So for each window, we calculate the Fourier transform, like here, and then we calculate the cross spectrum. So we just multiply the window, or the Fourier spectrum of this window, for the complex conjugate of the Fourier spectrum of a second window. So this we do it for all the frequencies, for all the windows. So we just sum them, and this is what we have here in the numerator. This is just the summation all over all windows for each couple of stations. Then the summation is simply normalized on the number of windows. And here in the denominator, we are normalizing for a factor that depends on the sum of the Fourier spectrum of each windows plus the sum of the Fourier spectra of the second windows. So, so this is just the summation above and below, and this is just a sort of normalization. So you can imagine if I would have only the same station within itself, here I would have a factor that is just the sum of the whole spectra, and the same I would have it here. So this function, when the signal is exactly the same, will give you a number 1. And then more different are the signal at the two stations, more this correlation function will change and will become smaller and smaller. The advantage is that in this case, with a single operation, we can calculate the correlation function for all the frequency in the spectrum, because we do it automatically. So for each distance, in this case, the distance between two stations, we have already the correlation function. So how similar are the signals for all the frequencies. Then if we change the couple of stations, then now we can make a station 1 with station 3, station 2 and station 3, and so on. We will have the correlation function for all the frequencies and also for many distance, as many a combination of stations I have. So, and this is represented here. So you see, these are just the correlation function that we obtain for different combination of stations. So each point that you see here is the correlation function for one station with respect to another station that I have in my array. And what you see here is just the value for each single frequency. So for example, I just select the value for frequency 0.9, for frequency 1.5, for frequency 2.5, and so on. So what you observe is that these values, just if you focus mainly on the black points, the gray are just outliers we can define, you see that the low frequency, as we expect, so the long wavelength, tend to lose similarity, let's say, the correlation is changing slowly with distance because they are long wavelengths. When we go more to the high frequency, we see that this correlation change more rapidly with distance. And we know from theory, from Aki, that this shape designed by these black dots, so by the correlation function, should approximate, should be the same of a Bessel function of 0 order. And this Bessel function simply depends on the frequency, that of course we can fix from the spectrum, on the distance that we know because we measure the distance between the station, and on the velocity at which that frequency is propagating. So how we can calculate then the velocity? We can do something, for example, very simple. We can test many velocities. For each one of these velocity, we generate a Bessel function. So one of these black curve, and we look at which of these Bessel function is best fitting the data that we just calculated. So for example, in the left panel, we see the Bessel function that is best fitting the black dots here. And we see this Bessel function here. In the bottom panel, what we have? We have the difference between each point here, each black point, and the black line. And we calculate the RMS. So we just sum up all the difference, we square it, we normalize on the number of points, and then we take the root square. So when the difference will be large, this value of RMS will be very big. When the Bessel function will approximate well our data, this value will become small. So what you see here is that if we take, for example, frequency 1.5, if I start with very low velocity for 1.5, my RMS, so my difference between the curve and the point, is very large. When I increase the velocity, this difference starts to become smaller and smaller and reach a minimum. Then if I increase the velocity again, this RMS is increasing again. So it means that for this velocity that is nearly 500 meters per second, I found the best Bessel function for fitting the data. So on the other terms, we can say, okay, this is the phase velocity for 1.5 hertz. So if you plot the correlation coefficient, so what we have seen now was just a slice. So we were just fixing a frequency and we were cutting in the direction of distance. But of course, you can also see the correlation coefficient for a fixed distance as a function of different frequencies. So we have an area where we have different values, area defined by distance and frequency, in which we have different correlation functions. So what you see here is that these are our observation, the changes of a correlation as a function of frequency and as a function of distance. And this is after that we made this research, the theoretical Bessel function for, let's say, the best fit velocities. And you see that they are relatively similar. So if now I have one velocity for each frequency, I automatically obtain my dispersion curve. This is an example where we can see that, as we generally expect, low frequency have higher velocity and high frequency has smaller velocity for the same reason that we discussed. So we can clearly see the dispersion. Okay, this dispersion curve, we know, is strongly related to the underground structure. And what we want to calculate is exactly the underground structure that is able to generate this dispersion curve. So again, if you remember from last time, we can have an inversion, and the inversion is able to find, let's say, the dispersion curve that, or the model that is able to reproduce to the best the dispersion curve that we obtain. This was one of the methods. So as we said last time, Aki is looking at the variation of a coefficient of correlation depending on the distance between the station and the frequency. So again, the velocity in this case is again related to the phase shift, like we have seen for the linear array data, but at the time we couldn't measure directly the phase shift. As a proxy for the phase shift was the correlation coefficient, because more we shift the signal, more the correlation coefficient will change. So when the two signals are really aligned, so the phase difference is 0, we will have a 1 in our correlation coefficient. When I start moving the signal and going more and more far away, the correlation coefficient is changing, is diminishing. So increasing the phase shift, we have this diminishing of the correlation coefficient. So it was a different way to measure the velocity accounting for the phase shift. There are other methods that are very similar to what we have seen for linear arrays that are working in 2 dimensions. So if you remember, in the linear arrays, we were calculating for each seismogram its spectrum, and then we were shifting the spectra until they were aligned.
È su Teams, non è alle 9:30, alle 9?
Ah, vabbè, ma vengo dopo. They will be aligned. So we shift, we change the signal until we have a maximum in the function that was summing all the signals after that we shift them. In 2D, we can do the same. In this case, this is a vector XL with the coordinates. So in this case, X and Y, because we are on a plane in 2D of a station, and this is the station, another station. So again, this term here is describing the distance between the two stations. In this equation, what you have the cross spectrum, the cross power spectrum between the two stations. So we just calculate the spectrum at one station, L, the spectrum at another station, M, like we were doing in the linear array. We correlate them, calculating the cross power spectrum. So spectrum for the conjugate, the complex conjugate of the other. And we change the phase using, again, an exponent. This exp E, kappa, you remember, is simply 2p divided frequency, divided lambda, so frequency divided velocity per distance. So again, we are just shifting, moving our two signal for a certain velocity in the X and Y direction, in the two direction, until we found the velocity that for each frequency is giving us the maximum of this function. So you have to imagine it's the same that we have done in 1D, but now we do it considering that the distance between the two stations is not only along the line, but is a distance between 2 points on a plane. Nothing else than this. The thing can also be a little bit more complicated with another method that is not as simple beamforming like the one before, which is called maximum likelihood method. That works in a very similar way, but you see here you have the inverse of the spectrum and here the inverse of this function that is calculated. This method is working a little bit better, but can be more sensitive to noise, but they are very equivalent, let's say, in the way they are working. So they have some difference in the windowing function of the data. I will not enter in this detail, but in general, what we can see is that the maximum likelihood is working a little bit better in terms of resolution with respect to the beamforming, but the maximum likelihood is more sensitive, let's say, to measurements errors. So if you don't have very good data, this can be more affected in the results. So even for then 2D arrays, we can apply these tools. So if we do this shift, what we get for each frequency, we will have a direction X and Y because I'm working on an array in 2D in this case. So I can expect that if the noise is coming from everywhere, for each frequency, I should have a maximum that is independent on the azimuth, but that is picked, let's say, at a certain distance from the center of these images. And you see here I have kappa x, which is the inverse of the wavelength in the x direction, and kappa y is the inverse of the wavelength in the y direction. These two factors, you remember, were in this equation. So if I move my spectra in the x direction or if I move the spectra in the y direction. And kappa, I remember, is equal to 2p divided the wavelength. And if you remember, the wavelength depends on the velocity and on the frequency. So again, we are simply moving as a function of the velocity. So these values that you obtain here, kappa, are depending on the velocity at which the waves are propagating. So if we pick the maximum in this diagram, we can calculate the velocity, exactly remembering that the velocity is equal to 2 times p for the frequency divided kappa. In this case, kappa is just the combination, because we are in 2D, of k in the x direction and k in the y direction. So it's just enough that I calculate the radius, so the distance from the center, which is the denominator. I know which frequency I'm analyzing. I can calculate for this frequency the phase velocity. An advantage of this method with respect to the SPAC method that we have seen before is that if the noise is not homogeneously distributed, but we have a noise source that is very well located in a place, then we can also estimate from the direction, the azimuth from which the noise is coming from. So we can also recognize a specific noise source reaching our array. And this is just a comparison of some dispersion curve and the dispersion curve, one in gray calculated with the SPAC method, and the other two calculated, you see, with the beamforming and with the maximum likelihood. And what you observe here is that in general, for the higher part of the curve, the two curves are very consistent. Generally, for the lower frequency that you can reach with your array, SPAC seems to work a little bit better than the beamforming and the maximum likelihood. So when the wavelengths are becoming long, so the frequency low, the beamforming and the maximum likelihood are less accurate in estimating the phase velocity. Okay. I will not enter in these details, but I want just to indicate to you that every array is like an antenna. So also with an array, like with a single station when we are recording our signal, we cannot record everything. Depending on the position of the stations, depending on their distribution of space, we can also have only a certain limited range of velocities that we can measure. Otherwise, we have the same problem that we describe in the time domain. So we can have spatial aliasing and not only temporal aliasing. And this is really one of the problems that we have to consider also when we do array measurements. There are some parts, for example, here or here, that are telling us which is the limit in between where we can measure the velocity at which waves are propagating. So we have to compare this transfer function of array with the results that we obtain to see if they are correctly estimated. Of course, this can also be corrected, like we are correcting for the instrumental response. We can also correct our images that we obtain for the response of the whole array. This can be done, and you see the red curve is our, let's say, section of the results before correcting for the instrumental response, for the array response, and you see that the peak here at which we have a propagation velocity of this frequency is not so clear. When we correct for the response of the whole antenna, let's say, the peak is becoming more clear and we can better estimate the velocity. But very often this is not used. So in general, we can say that these methods these methods that we call FK method has some advantages. One advantage is that they can check also the azimuthal distribution of a noise source at each frequency. The SPAC or ESAC method in general seems to work better, especially for the low frequency range of our signal. So they allow us to investigate deeper, but they work better if the noise is stationary in space and time. So if we have also a good azimuthal distribution of noise source. So it's good, in my opinion, generally to combine the two methods. So the FK method can tell us if this condition that the distribution of noise source is stationary in space and time is valid. And then if this is confirmed, we can apply correctly the SPAC or ESAC method, and therefore to obtain a dispersion curve that probably is a bit of higher quality, especially for the low frequency of what we can get from the FK method. So summarizing a little bit, when we go in the field, we deploy some station on the ground. Just imagine we go in the garden of your institute, you position, for example, in this case, stations on the ground in an L-shaped array. And then we are recording noise, you see here, at all the stations. At each station, we will calculate the spectra of a signal, and we will look at all the possible combination of stations. So what is the similarity, for example, of the spectra recorded at this station with this station with this station, and so on, all the possible combinations. So in the ESAC method, once we calculate the spectra, what we do? Okay, we just calculate the cross power spectrum and we normalize it, and we get some correlation coefficient as a function of distance and of frequency. In the FK, again, in principle, we are calculating the cross power spectrum. And from the cross power spectrum, then we shift this cross power spectrum until we found the velocity that is summarizing, providing the maximum value of the summation that we have in this integral for all the possible combination of stations. In the SPAC method, we will take this coefficient and we will fit them with Bessel functions. So for each frequency and for each distance that we know, we can calculate different Bessel function for different velocity, and we will keep the Bessel function that is best fitting the data. And this is giving us a dispersion curve. Here, we shift all the signal, we sum up them for different shifting depending on the velocity that we will use, because kappa, we said k here depends on the velocity, and we will obtain images like this that as a function of a k in the x direction or in the y direction are showing a maximum. I pick the maximum, so I take its distance from the center, and then for this frequency, I can immediately calculate its velocity of propagation. I can also, of course, calculate directly from the kx and ky, the angle theta that is telling me from which azimuth my noise is coming from. Okay? So now we come back to the point of direct and inverse and forward and inverse modeling. So I don't think I have to repeat this part in the general part because we see it last time, but we can come maybe more to the problem directly of the inversion of surface waves that we have seen a little bit last time. Just make it simple. Generally, when we invert for a dispersion curve, we invert both for the velocity and the thickness of the layers. Here, I assume that we know the thickness of a layer of the underground, and we want to check only their velocity. So if I make a linearized inversion, I will have data that are my observed phase velocities. My unknown are the velocity, the shear wave velocity in the underground. And I have to find a link between the shear wave velocity in the underground and the observed phase velocity. What is the link? Is this Jacobian matrix that is telling us how much, if I change the velocity in one layer, the phase velocity at each frequency, you see in this case, in this column, for the frequency, for different frequency, how much my phase velocity is changing. Then I can change the velocity in another layer, and this column will tell me how much the phase velocity is changing if I change the shear wave velocity in a certain layer of the underground. So we have seen it a little bit already last time. And we said then we have this linear system. In reality, my data are not the observed value, but are more the difference between the observed value and the value that I can generate for a first model that I use to start my inversion. And then my unknown will be the adjustment in the shear wave velocity in the underground that are necessary to improve the model until when I get a calculated phase velocity, which is very similar to the observed one. Okay? So we have seen last time that this, for example, how to calculate this, I start from a model of the underground. For this model, I can calculate the first dispersion curve that you see. It's not able to reproduce the data. So it means that the model is not an appropriate description of the underground. So I have to modify this model until I will get a curve that is fitting the observed data. So the first thing is, okay, I calculate the difference. These are my observation, the difference between the observed data and the calculated one. And these are my data that I will use to find the right adjustment. But first, if you remember, we said we can do it for the H over V, but we can do it as well also for the dispersion curve. We have to calculate the matrix that is linking the changes in the velocity, in the shear wave velocity, I repeat, in the underground, with the phase velocity of Rayleigh waves, for example, in this case. So how can I do it? I said I have a starting model. So what I can do, I just modify the velocity of a first model. So I can calculate these partial derivatives numerically. So I just modify the velocity in the first layer. And therefore, for this new model, I can calculate a new dispersion curve. And if I take the difference between the original dispersion curve and the new one, I will have immediately the changes that are expected due to this new model. So this is telling me, depending on the change in the velocity, how much my phase velocity will change. And I can check this for all the frequencies. So if I plot it here for visual, so I'm changing the velocity, in this case, in the first layer, so layer number 1. And this is the changes of the phase velocity at each frequency in my spectrum. Okay? If I then want to calculate the second part of the partial derivative, I can do the same, modifying the velocity in the second layer. Again, I calculate a second dispersion curve. I check how much this dispersion curve is is affected by the changes in the shear wave velocity. So I look at the value for each single frequency that I have in my dispersion curve, and therefore I get a second row. And I can repeat this for all the layers. Here I include not only the number of layers, which is 1, 2, 3, 4, but also their thickness, just to tell you also a feeling of how much a frequency can see in the underground. What we see here, again, it's very important. This is our Jacobian matrix that is showing what? Is showing that, for example, the high frequency can only see, you see, especially the highest one, above 4 Hertz, they are only sensitive to changes in the shallow structure. So below, I can modify the thickness of the velocity of the layers, and I will have no influence. While the low frequency, for example, the lowest one at 1 Hertz, they are a little bit less sensitive, you see, in the shallow part, but they become much more sensitive in the deepest part. So, and we remember this is due exactly to the dispersion and to the different wavelengths and depth of penetration. So then, using this matrix, I can make a different kind of inversion. So I can make a linearized inversion in this case, for which I can start from different models. So these are my different starting models. I perform my inversion until I fit the data, and I will have, for example, a bunch of models like this. You see where all the models are converging. This is telling us that the solution is relatively robust, so we can trust it. In the deepest part, you see that even if I make an inversion, the solution is quite sparse for the different models. It means it's not very well constrained. So if I should interpret these results, I would trust the results quite a lot down to 180 meters, and I would not trust too much the results in this deeper part. So be very careful, and it's important if you use especially a linearized approach, like in this case, it's good to test always different starting models in order that then you can really assess also how robust is your solution. Of course, there are also other tools that you can use directly, resolution metrics and so on, that there are mathematical tools that can tell you how good is your solution. And this always has to be checked. So please don't trust your results without any criticism, but always look a little bit also to the resolution and to these parameters before interpreting them.
Hello, Professor.
Yes.
I have a question.
Yes.
It is related to the starting model. If we do not have any information like prior information about the area, so then we can we give a larger domain and then check where these parameters are concentrating or converging, so that
yes, there is always the risk of, you see, since your solution, it's a nonlinear problem. So if you start too far away and you linearize, let's say you start from a model here.
Yeah.
when you start a linear inversion, then in this case, you would converge to the absolute minimum. But if you would start, for example, with a model here and then you linearize, you would be stuck in a local minimum of a solution. So then it's good to test, that's why it's good to test the different models. But how different can be from reality? I think that there is a rule of thumb that can be followed. It's very rough, it's very practical, but can help you in design the first model for the inversion, just not to start from completely crazy data. And the rule of thumb, I'm just checking for a dispersion curve, can be something very simple, like, just go to the original dispersion curve. I don't have a dispersion curve anymore. No? Okay. Okay, here. What you can do. If you remember from last time, we said that the depth of penetration, it's nearly identical. Okay, it corresponds to lambda divided 2 lambda wavelength divided 3. Okay. So how can I have an idea of the velocity profiles looking at this? Okay, the first thing I can do, I can transform this dispersion curve in a curve that is giving me velocity as a function of depth instead of frequency. And how I calculate the depth? I first calculate the wavelength that I know is velocity divided frequency. This gives me wavelength. I divide it for 2, and I have, let's say, a reference depth for this frequency. At that depth, I will assign the value of velocity, let's say a little bit modified, 5% or something like this, to take into account of the difference of velocity between Rayleigh and shear waves, okay? So you can directly from the dispersion curve to have a first idea of the shape of the velocity profile. Is it clear? No?
Yeah, it is clear.
Okay.
Yeah,
and this will tell you more or less the range of value of velocity. Then you can do what has been done here. So you have this reference profile that you can separate in some layers. And then you will start the inversion with different models, a little bit faster than what you get, a little bit slower, and so on. No, like here, start with a model. Let's say my reference profile is the red one. I have a model which is a slightly smaller velocity and a thicker, slightly higher velocity and thinner, and so on, all the possible combination. And then you perform your inversion and you see how much it can be reproduced. And generally in this way, you have reasonable starting models, let's say, even if you don't have other information, and generally reasonable results from your inversion. It's a rule of thumb, but I think can work relatively fine, at least for defining a set of starting models that you can use. It's clear, this?
Yeah, it is clear. Thank you.
You're welcome. Okay, so we have seen also already that since, like I said, it's a nonlinear inversion, what we can do is just to perform a nonlinear inversion. So we have seen this with modified genetic algorithm, for example, where instead of starting from one model and then moving it through a linearized inversion, we generate a bunch of models within a certain range of velocity and within a certain range, in this case also thickness. And again, also in this case, how large is the range for each depth can be defined with the same rule of thumb that you have, that I was describing before. Each model is described in his parameters so velocity or thickness, through a binary code. And for each one of these models, we generate its dispersion curve. We will observe that there are models providing a good approximation, a reasonable first approximation of the dispersion curves, and models which are completely out. Now, how can we proceed? Okay, first we look at, again, how good are the models with respect to the observation. And we can calculate what we call a misfit function that is describing the distance between the observation and the calculated model. Of course, smaller the misfit function is, because it's smaller this difference in green, higher will be the fitness that we calculate here. So in principle, since it's a genetic algorithm, we already described it, we will try to have the models or parameters of the models with the best fit that survive in the next generation of models. And for doing this, what we are doing, we calculate first the probability of each model to be reproduced. And as we said, the probability will be higher for the models who have a higher fitness, because this is the fitness of the model divided the summation of the fitness of all the models. So the models that contribute more to the total fitness will be the one with a higher probability to be reproduced. So for generating new models, and generally the one with higher probabilities, for example, are here, the ones which are providing a curve that is closer to the red one. So for deciding who is surviving and how to generate new models, there are two genetic operations that I described already last time. I will go a little bit faster today on this, but I want you to refresh this. And they are called crossover and mutation. So the crossover, what is doing? So we randomly select first the models, and generally we will fish from our distribution, probably because they have a higher probability, the one which are already providing a good dispersion curve. And we take one part of their features and we combine it with another model that we fish. So we generate a new model, which is a combination due to the random combination, let's say, of two models that we fish from our distribution of models, taking into account their probability of being reproduced. The mutation is not mixing the two models, but is acting directly on the model itself that we can take. And what is doing, again, randomly, is swapping one of the bit in our parameter. And this can have a strong influence on the changes in the model. So after this operation, we have a new generation of models that we expect generally to be better than the previous one. For each one of these models, we recalculate the dispersion curve, and so on until we find the model that best fit our data. I mentioned already last time that we have also two operations. So if we would generate only random models, it would take a lot of time before the solution converge. So to do a little bit faster convergency, generally we use an operation which is called elite selection, that simply means that the best model in each generation is reproduced in the new generation without any modification. This is a risky operation because maybe can lead us to be stuck in one of these local minimum of a solution. So what we are doing, if we see that after many iterations, the best model is always this one, we have a suspect that maybe we are in a local minimum of a solution. So we let the mutation to become more often. So we increase the probability of having mutation. So we can also generate models that are very different. in order to explore better the space of a solution. So this is an important way to estimate the underground velocity. There are two aspects that we have to consider. That generally the velocity is not only increasing gradually with depth, but we can have low velocity layers. So the velocity can have inversion. Inversion means that we can have in our dispersion curve a strong influence of the higher modes of propagation, for example, of Rayleigh waves, like you see here. So if a model is increasing regularly with depth, you see all my dispersion curve observed, which are triangles or dots, it's strongly dominated by the fundamental modes. So the higher modes at which each frequency is propagating are not playing a role. But if I have a sandwich layer, like in this case, you see decrease of velocity and increasing, in some frequency range, my dispersion curve is neither belonging to the fundamental mode nor to the first or second mode. It's just a sort of apparent velocity that is crossing different modes of propagation. And the same can happen also when it's deeper the layers. So you see in this range, it's not the second mode or the fundamental mode that are playing a role, but just a combination of two. It's like if energy for the same frequency propagating at different velocities arriving all together. So we are not able to separate this. And this effect has to be taken into account when we are doing the inversion. So if we are trying to invert a dispersion curve like this one, forcing it to describe it with a model under the condition that everything is the fundamental mode, our models would be very much presenting large artifacts. So generally what we use is what we call apparent velocity. So at each frequency in our dispersion curve, the velocity is a combination of the velocity of the different modes, here indicated with M, depending on this function A, which is the medium response to the mode. You can imagine it's more or less the amplitude, you can see it as sort of a Fourier amplitude of each mode. So we waited to see which mode is more important in the generation of our dispersion curve. So this seems to be something maybe not so important, but in real cases, especially for shallow velocity profiles where we have inversion of velocities, the inversion should be able also to take into account the fact that higher modes can play a role. Otherwise, the results could be very, very much biased. An important part was that 15 years ago, what we proposed was also to make a joint inversion of phase velocity and h over v. So if you remember, h over v, it's a good tool for investigation, but we said suffer of trade-off between velocity in the sedimentary layer and thickness of the layer. We have to fix one of the two. The Rayleigh wave velocity, for example, since close to the fundamental resonance frequency, the vertical component is going to zero, has another problem. It's very good in fixing the velocity in the sedimentary layer, but might have problem in seeing the bedrock or the bedrock position. And we know that in this the h over v is very good. No, it's very good in seeing the bedrock and in providing a peak that corresponds nearly to the resonance frequency. So the idea is if we combine in the inversion h over v and dispersion curve, we can take the advantage of one to solve the problem of the other one and to have the best solution. So we could improve the model that we obtain. So you can see it a bit in this way. The dispersion curve will allow us to fix the velocity in the sedimentary cover. Since the velocity is fixed, then the h over v knows the velocity can fix very well the thickness. So combining the two things, we can probably improve the models. And that's exactly what's happened. These are just some example of inversions, but these I probably can skip it, just a test that we have done in many places, combining different techniques. But the important point I wanted to show you is, okay, we had many applications. You see, this is in Istanbul. So you can have your arrays even in football field in the middle of a town. And the data that you get are generally very good. I wanted to tell you something maybe more interesting today, that not only you can make the Rayleigh and H over V curve inversion, but since now we are working mainly with free component sensors, it's also possible to estimate from the wave field the Rayleigh and the love wave velocity. And so if we can extract, and this was already proposed by Aki, so in a very similar way, as we have done for only the Rayleigh wave, it's possible to calculate correlation coefficient for the radial component between the two stations and for the transverse component of motion. You know, we have a free component sensor recording vertical and two horizontal components. So we rotate the component between the two stations and we can calculate then also radial and transverse motion. Transverse motion is related to love waves. So it's possible to calculate this. We need some assumption, or something that we can also calculate is the ratio between love and Rayleigh waves in the wave field, which is described by this parameter alpha. And you see that this ratio is strongly frequency dependent. And therefore we can calculate from our arrays H over V, Rayleigh, and love curves. And we can then invert, so look for a model that is able to describe the Rayleigh wave curve, this one in blue, the love wave curve, this one in green, and the H over V at a certain site. The question could be, does it make sense? And the answer is coming from these free Jacobian metrics, which are calculated exactly as I showed you before. What you observe here is that the sensitivity in this frequency range for Rayleigh waves is very different from the one of love waves and the one of H over V. So, like we said before, Rayleigh waves are sensitive to, in the high frequency part, to a shallow part of the underground, but also down to, let's say, 15 meters here or something. And the low frequency part is more sensitive to deeper part. The similar behavior have love waves, but you see the love waves are much more sensitive to the very, very shallow structure. The H over V is sensitive to the underground structure in a very completely different way. So it's very sensitive at frequency closer to the resonance frequency because we have a peak. So if we just slightly change the velocity of one layer, the peak will completely move. So we will have a very large change close to the resonance frequency. And it's very sensitive, especially to a change in thickness at a frequency, at a depth that is compatible with a large impedance contrast. So since the three different curves are sensitive in a different way to the underground, it makes sense to invert them because they provide different information on the underground structure. If these three metrics would be identical, I would not add any information. I would just repeat. Makes no sense. But in this case, they offer different view on the underground. And so inverting them, it's allowing us to find a model that is better of the underground because it has to be able to explain all these three different curves. And you see this here. You remember I showed you two different models last time with the same H over V, identical. Someone asked me, but where is the other color? It's just below. But these two different models have the same h over v, but they have two different Rayleigh waves curves. So it means, okay, before using only the h over v, I was not able to understand what was the difference in this model. But now, if I combine this inversion, I can distinguish these two models. Okay? So for today, we stop here. Do you have questions about it? No question? It's all clear? I think this part should be very clear because it's important for you in general. You can apply to dispersion curve to h over v, but in many other problems in seismology or in geophysics or in physics, whatever. So if you got to the point, you can easily then apply this also to other different problems. Any question? Okay. Then I guess everything is very clear, I hope, or very unclear. But this was also to repeat a little bit what we have seen last time, because maybe this is a little bit more complicated. I wanted that you got a little bit more about this concept. So no question? Okay, then we see directly on Monday, and I wish you a very nice weekend.
Yeah.
Okay?
Thank you.
Bye-bye.
Grazie, buon weekend.
Bye.
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 Grazie, arrivederci.